Today we want to explain Kruskal's algorithm. Kruskal's algorithm is part of the graph theory. We have a graph with edges. The edges have a weight, so there's a different cost from going from one edge to the other. And we want to find the minimum spanning tree, which is the way to connect all the edges with the minimum weight. Kruskal's algorithm is a series of steps which will give me this result. Remember that the minimum spanning tree is only unique in a graph if all the edges have different weights. If there's edges with or paths that have the same weight, you might have 2 or 3 minimum spanning trees which are valid and are equivalent. And we'll see it in an example afterwards. Okay. So an algorithm is just a series of steps. Which are the steps of Kruskal's algorithm? Well, we're going to start with the edge with a minimum weight. If there's various, well, we just start with one of them. We will go then to the next edge of minimum weight. We will check if it creates a closed circuit, a loop. We don't want loops, so if it creates a loop, we're going to discard that path. If it does, we discard it, and go back to step 2 until the graph is finished. Okay. The easiest way to do this is to just show you how to solve one of the graphs. So there's various ways to do this. I'm going to solve the 2 exercises that I'm going to show you today in 2 different ways. As long as you follow the algorithm, it doesn't matter how you do it. And I'm just giving you ideas on how to solve it better. So, but the idea of Kruskal, remember, is to always start with the minimum ones, okay? And discard any closed circuits. So what I like to do sometimes is just write all the edges from the minimum weight to the maximum weight in order. So let's start here. We have AB with a weight of 2. We have DE with a weight of 2. Then we have we had FG with a weight of 1. And we have BE with a weight of 3. We have BF with a weight of 3. We have BG with a weight of 4. And AD with a weight of 4. 2 4s. Then we have a 5, which is the AF. Then we have a 6, which is the CG, which is a 6. Doesn't matter the order of the letters, you just have to know which path you're talking about. There's only one 6, and then there's the 7, which is BC. So 7. And then we have a 10, which is EC. Always count that you've got all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Got one missing. So 1, 2 2s, 3, 3. There's a 4. There's a 4. There's another 4. There's an AF. There's a 6 here. Oh, there's 2 1s. There's BD. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got all of them. So what am I going to do now? I'm going to start with the minimum ones. Remember, it doesn't matter if I start with BD or FG. I'm going to put them in my spanning tree, so I can do it on the same graph or just create another path. BD is going to be included because it is the one of the minimum, and I just like to tick it there. And FG, which is 1, I also include that one. AB is the next one, and that is included. And DE is the next one, and we include that too, okay? Now, we start having problems. If we included AD, which is not in order, but if we included AD, that would create a closed circuit here. This one, okay? So I don't want that. I can't. So I can already discard AD. I'm not going to use it. For the same reason, I can discard BE, because it's going to create a closed circuit. Let's go to the next one, BF. BF seems fine. I'm going to tick it. BG cannot be included. It will create a closed circuit, so that's off. AF creates a closed circuit, off. CG is okay. And a ticket. BC is a closed one with all this loop, so that's off. And EC is a big closed one too, so that's off. So I already have my minimum spanning tree, which is this one over here. If you want to write it down, you can have it here. E, D, B, A, F, G, and C. And you can see that I can reach all of the edges. They're all connected. And this one is the one with the minimum weight, because I've started with the minimum ones. What is the weight of my minimum spanning tree? In this case, where I just have to add the ones I've added. 1 plus 1 plus 2 plus 2 plus 3 plus 6. So that's 1 plus 1 plus 2 plus 2 plus 3 plus 6. Yeah, so that's 1 and 1, 2, 4, 6, 12, 15. The weight of my minimum spanning tree is 15. That's easy. Okay? Remember, it's a tree. It's not a path where you can close the whole path and go back and forth. It's a tree that connects all of the edges. Okay? So let's do another exercise. This is a bigger one. And I'm going to solve it in another way, just to show you that as long as you follow the algorithm, the steps, start with the minimum, go to the next one. If it creates a closed circuit, discard it and go to the next one. You can do it any way you want. So I'm going to do it directly on the graph. So what's the minimum here? The minimum here would be this path of 2. So I'm going to start with that one. Then the ones of 3 and the 1 and 3 here. Perfect. That's correct. Now we would have another one. Is there a 4? No, there's a 5 here. That's perfect. I can go I can go to the 6 and I can close this 6. Perfect. And now I have neither of them create any trouble, and I have 2 7s. And I cannot close both, because if I close this 7 over here and I close this 7 over here, I have a closed circuit. So I can only choose one of them. Which one? Doesn't matter. We will have, if I close this one, I can continue the spanning tree and have one minimum spanning tree. And if I close the other one, I would continue the spanning tree and have another minimum spanning tree. So in this case, as the edges don't have all different weights, and there are some paths with the same weight, we can have minimum spanning trees, different minimum spanning trees, and they're valid. Okay, so they're not unique if the paths don't have all the different weights. So I'm going to choose this one. Why? Because I want it. I cannot close the 8 because it creates a closed circuit, but I can close this 8 over here. And I can close this 8 over here. I cannot close the 9 because it would create a closed circuit. I can close this 9 over here. I cannot close this 10. It's a closed circuit. I cannot close this 10. It's a closed circuit. Cannot close this 10 either. So no 10s there and no 10 here. I cannot close this 12 over here because it creates a closed circuit, and I cannot close this big 12 over here because it creates a closed circuit. And the 13, I cannot close it because it creates a closed circuit too. So I'm finished. I've created a minimum spanning tree, and the weight is going to be the addition of all those, which is 8 plus 5 plus 9 plus 3 plus 7 plus 2 plus 6 plus 3 plus 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 5, 9. 3, 7, 2, 6, 3, 6, 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is 57. So the weight of the minimum spanning tree is 57. Remember, if I had chosen the other 7 instead of this one, I would have gotten the same spanning, an equivalent spanning tree with the same weight, because I would just substitute 1 7 for the other, and it would also be a minimum spanning tree. Both would be valid. Okay.